Good afternoon, sir.
Good afternoon, ma'am.
Dear participants, our next speaker has joined us. As per schedule, Dr. Yashash Chand Trivedi from the NIT Kurukshetra have to take the session, but due to some health issues, he will take the session on the Friday. So we are with us, the resource person of this session, Dr. Shobi Bagga from RTU Kota. So before starting the session, let me give a brief introduction about our expert. Dr. Shobi Bagga received the BE degree in Electronics Instrumentation and Control from the University of Rajasthan, Jaipur in year 2000, MS from Indian Institute of Science, Bangalore, India in 2007, and PhD from Rajasthan Technical University, Kota, and Center of Electronic Engineering Research Institute, that is Siri Pilani, in year 2020. In PhD, his research work has mainly focused on the development of MEM-based gas sensor, while in IISc, his research activity was focused on development application-specific integrated circuit for sensor interface. Currently, he is working as assistant professor in Center of Nanotechnology RTU Kota. He has several research publications in international journals and conferences. He also worked as research and development engineer in the FPGA design group of Tejas Networks Private Limited, Bangalore, India, prior joining RTU, where he was involved in the design and development of FPGA for various networking related products. So, sir, we heartily welcome you in this ATAL FDP on recent advances in nanoscience and nanotechnology. And the mic is over to you, sir, for the session.
Thank you, ma'am, for the introduction. So, good afternoon to all the participants. Now, should we start or wait because there are?
Sir,
Can we
you can
start now?
start. Meanwhile, the students will join.
Okay, my start then.
Yeah, participants will join meanwhile.
Ma'am, screen is visible?
Yes, sir.
Okay. So, good afternoon to all. Today I am going to deliver a talk on the development of the nanostructure chemiresistive gas sensors. So prior to starting, I want to know about the students. Are you comfortable about the gas sensor? Do you have any idea? Yes, among the audience? So let me do it two-way talk instead of the one-way talk. I will just represent and you will listen. That will be interactive if you talk we talk with each other. Yes? Anybody have any previous experience on the sensors? My voice is audible, ma'am?
Yes, sir, you are audible. Dear participants, make it a please a two-way talk. If anybody knows about gas sensor, he can respond.
That would be better. Otherwise, I will deliver from my side. I want to know from your side also. Somebody
Of
can
course.
share.
No, sir, not specific about gas sensors.
Okay.
Just pressure sensors. We had some simulations
Okay.
done using counterware. That's all.
Okay. Okay.
Yes,
Okay. Good.
I have idea about a gas sensor.
Okay. So have you done any work on that previously?
Yes, sir, I have done on zinc oxide as a gas sensors for especially oxygen sensors and some also ethanol sensor.
Okay. Good. So let me start the talk. That is development of the nanostructure chemiresistive gas sensors. Prior go into the detail about the how to develop the chemiresistive gas sensors. I just give you a brief introduction about what is the gas sensor, how it works, what are the different generations, what are their applications, and what are the main requirement to develop the sensors, gas sensor particularly. So gas sensors like recognition of a particular kind of the gas. The first thing comes how the sensor works. Whenever the gas comes in the contact with the particular sensor, particularly gas sensor, there are two things are there. First, sensor has to sense, that is known as a receptor function, means it has to recept the gas, and then transduction function, that is conversion of the recepting gas into the particular sensor signal. That sensor signal may be the change of resistance, maybe change of the capacitance. It depends upon to the particular kind of the gas sensor which we are going to develop, right? So our main interest is to detect this sensor signal, because that will give me the information what kind of the gas and what is the quantity of the gas is coming in the contact with the sensor. That is a function of the sensors, right? So if I summarize, in the recepting functions, only the surface is involved, while if we see in the transduction conversion, whole sensor is involved to conversion of the electrical signal, because we are mainly interested to detect the signal that will give me the desired information or desired type of the gas, desired quantity of what is the quantity of the gas. Fine. So if we see the different types of the generations are there. First is this Tegachi based sensor which was developed in 1956. That was basically consist on the ceramics, this cylindrical tube. You can see it over here. That is ceramic tube. In this one heating coil were there, and sintered tin oxide was coated, and this tin oxide has the mainly used for detecting the different types of the gases, because whenever it comes into the contact with the different type of the gas, it changes its resistance, and change in the resistance basically depend upon to the how much quantity is there and which type of the gas is there. So by detecting the change in the resistance, we can identify what is the type of the gas and what is the quantity of the gas, and through these electrodes. But the main problem with the first generation sensor was this: it has a size was big and power consumption was high. So that's why in order to reduce its dimension, to reduce the power consumption, 2D type of the sensor was developed. That is basically, instead of using the cylindrical tube, aluminum substrate is used and sensing element coated onto the one side and heating element coated onto the another side. We can see it over here. And electrodes are used to detect it. And in further advancement of it, to reduce the power consumption, to increase its sensitivity, to selectivity, MEMS based sensors was developed by different kind of the company. So these are the few pictures, but I will try to show you how these sensors are basically developed, and what kind of the devices or what kind of the skills are required to develop these sensors. The main outcome of this lecture may be, if somebody wants to develop or start is startup to develop the sensor, then he or she may use this technology to develop the different types of the sensors. So what are the applications? There are plenty of application exist. For example, if we want to determine the hazard gas, where the human person can't go, automatic recognition should be there. For that purpose, gas sensors have the applications. If you want to monitor the pollution monitoring, pollution, because nowadays, because of the global warming, we need to monitor the environment, or we have to control the pollution. So for monitoring the pollutions, gas sensor require extensively. Fire or smoke detection sensors are there. E-nose, I think most of you know, E-nose is basically nothing but a consist of the series of sensors to determine the different kind of the gas, like a human being. अपनी नाक होती है, that is nose, that develop in the laboratory, that we call it as a E-nose, that is electronic nose. For the home security, for example, we use the LPG gas for the cooking applications, and nowadays we are using the LPG for the driving the vehicles. So if we are not able to sense it at early stage, then explosion may happen. So for that purpose also we require the sensors. In this present work, we will basically focus on to the LPG detection through the tin oxide. And next one is the breath analysis. Breath analysis, it has a plenty of future applications which can go, gas sensors can go toward the biosensors. We will talk it in detail about in the next slide about the breath analysis, how it can be used, how the gas sensors can be used to determine for the breath analysis, and what is the requirement. Now the main requirement of the sensors should have the low cost, first and foremost requirement, which should be the hardly a 25 paisa or the 1 rupee sensor. Power consumption should be low, so that using the battery, should have the life 5 years, 6 years if we are using the battery, because of the low power. It should have the high sensitivity, that's in the ppm range, high selectivity, and at the same time small size. To fulfill these requirements, scientists are forced to use the MEMS or the NEMS technology to develop the gas sensors. As I told you, what is the breath applications? कैसे gas sensors काम आएगा अपने? Like if we go to the doctor कि भाई मुझे particular disease है, and then doctor writes some kind of the test that is invasive type, take out the blood or the imaging type to determine the particular disease. But by utilizing the gas sensor, just by analysis the breath, we can determine what kind of the things is going on inside the human being. How? Let me discuss about that. Among these applications, human disease detection through analyzing patient breath has attracted enormous detection attention in the past decade due to its key advantage over traditional diagnosis method. Like traditionally अपने को blood निकालना पड़ता, that is invasive. While if we are analyzing through the breath, that will be non-invasive in nature in the real-time analysis. Second thing, human breath basically consists of the oxygen, nitrogen, carbon dioxide, nitric oxide, ammonia, water vapor in addition to the more than 1000 volatile species with the concentration ranging from the several particles per trillion to several particles per million, including ammonia, acetone, ethanol, acetaldehyde, and propanol. Among this, whenever there is certain kind of the disease to the human being, particular amount of the gas may be increased in this breath. So by measuring that, we will be able to determine how the person or the patient is suffering from which kind of the disease. The concentration of the indigenous component, including organic gases, volatile organic compound, can be altered in the breath of the patient with specific pathology, and that can be utilized as a breath makers for the disease. So by measuring the gas, we can detect what kind of the disease may have. For example, acetone, hydronic sulfide, ammonia, nitric oxide, toluene can be used to evaluate the diabetes, health, kidney malfunction, asthma, lung cancer specifically. Whenever the kidney malfunction occurs, there is a level of the phosphorus varies. So by detecting these volatile compound in the excited breath act as a target for sensor and according to can be used for diagnosis tool for the related disease. So gas sensors are not specific to determine the pollution monitoring. It has a huge potential for the as a biosensors for the health monitoring of the person, and that important advantage, it will be low cost and non-invasive. Again and again, and the probability of the error will also be less. So that is the huge application in the future. Somebody want to work in that arena, it has a huge potential. Now, what are the different types of the gas sensors are present? We may have the different types of the gas sensor. I have taken only few, but apart from that, there are plenty. Optical gas sensors, thermal gas sensors, acoustic type gas sensor, or the chemiregisters. Now, if we see in the optical gas sensor, basically we use the optical fiber, which tip is coated by the fluorescent dye with some kind of the polymer matrix, and whenever the gas comes into the contact, it function changes. So that is the optical type of the gas sensors. It has certain advantages. Its lifetime is long, good stability, independent on atmosphere, while it has certain disadvantages. The main disadvantage, its large size, and it is difficult to miniaturize. That's why we are not going to use the optical sensor for development of the LPG, for the LPG or the gas sensors. Thermal gas sensors are basically works on the basic principle of the exothermic or the endothermic reactions. So whenever the catalytic containing heating element gas comes into the contact, it changes its temperature, and if we are able to detect the change in the temperature, that purely depends upon the which kind of the gas and what is the concentration of gas is there. They are stable at the ambient temperature, cost effective, sufficient sensitivity for the industrial detection. But the main problem is the risk of the catalytic poisoning and explosion, because we are going to use the high temperature, and intrinsic deficiency in the selectivity. Petrochemical plants, mine tunnels, detection of most combustible gases use basically the thermal sensors. Acoustic sensor can be bifurcated into two parts. First, as you must have heard about bulk acoustic wave and the surface acoustic waves. Acoustic waves means whenever there is a change in the frequency, that will depend upon to the what kind of the gas is coming. It has lifetime, high lifetime, secondary pollutions are not there, but it is less sensitive, and it functioning is also depends upon to the environment. So whenever we want to develop the wireless sensor network, it has a huge applications. If it comes onto the chemiregister, and these chemiregisters are basically mostly used for the development of the gas sensors. It can be bifurcated to two parts, or in some cases, these two are combined. First is the carbon nanotube based, and second one is the metal oxide semiconductor base. All of you know that CNT has the excellent absorptive capacity due to large surface to volume ratio. short response time, and its sensitivity is quite high, but it is not economical and it is really difficult to synthesize, because if you want to develop the single wall carbon nanotube, then it's not an easy task. It has a plenty of application like partial discharge detection use. While metal oxide semiconductor, why we are calling it is a chemiresistor? Because whenever the gas will come into the contact with this, its resistance will change. That is because this chemiresistor consists on the two words. One is the chemical and second one is the resistance. The two parts combining. So whenever any chemical substance, that is basically gas, comes in the contact with these materials, either carbon nanotube or metal oxide or mixture of both, then their resistance will change. And this change in the resistance is a mark for how much gas is coming and which type of gas is coming. That is selectivity, and first one was the sensitivity. So this metal oxide sensor is cost effective. Its cost is very low. Response time is low, long life, sensitive to different types of the gases. But the main problem, it consumes more power. To avoid this more power consumption, we try to develop using the nanomaterials through the MEMS. So power consumption can be reduced. Another problem with the metal oxide semiconductor, that they will become active only at the high temperature. So we have to heat it. To heat it, instead of using the bulk heater, we try to develop the micro heater so that power consumption should be very less. To overcome the selectivity and sensitivity issue, we try to use the different types of the either doping or using the CNT to increase the selectivity and sensitivity. To avoid the humidity, we try to use the different types of the filters or different types of the humidity material to avoid it. It has a plenty of application, domestic, automobile, as well as it has an industrial use. So in this presentation or in this today talk, we will try to focus mainly on to develop what are the metal oxide sensors, how it works, and how we can develop a product based on the metal oxide semiconductor gas sensors. Because its advantage as already it is low cost, response time is good, long life, it is sensitive to different types of the gases. But the problem which is low power consumption, we try to reduce it. Selectivity, we can increase the selectivity, sensitivity, and we can eliminate the humidity. So its cones can be easily removed as compared to the disadvantage of other types of the sensors. So therefore, we are trying to develop the sensor which is based onto the metal oxide semiconductor. Till now, any doubt to anybody? Yes?
No, sir.
Okay. So let I explain you how this metal oxide sensor works. If we see, these are the certain kind of the grains. I think most of your material science, they must know about the grains. I will show you the same images also to you. What happens when we keep it into the atmosphere? Every type of the metal, that why we are calling it metal oxide, metal and oxide semiconductor. Its name is metal oxide semiconductor. Metal means it may be tin, zinc, titanium. We have the different types of the metals. Whenever we form its oxide, now all of you know that oxygen has the tendency to attract the electrons from the materials. So whenever this atmosphere oxygen comes into the contact of this material, it takes out the electron from this reaction, which we can see it over here. This oxygen will come into the contact with this electron and charge it. So there is a deficiency of the electron, due to which the Schottky barrier height is increased. We can see it over here. These are the grain boundaries. Here we can see the boundaries on the grain to grain boundaries. The barriers are there which work as a barrier for the flow of the electron from one grain to the another grain. So on the boundaries we can see the barrier height is increasing because oxygen is making the reaction with these electrons. So here we can see. Now, whenever the reducing gas, for example, our petrochemical gas, methane, ethane, propane, butane, or carbon monoxide gas, come into the contact with this charged oxygen, species oxygen, it liberates the electron so that the barrier height decreases. And this decrease in the due to this decrease in the barrier height, the electron can flow from one grain to another grain very easily. So we can say more and more electrons are coming whenever the gas is reacting with this. So and when the flow of the electron, more electrons are there, resistance will be less. So what we can say, whenever the reducing gas is coming, the barrier height is decreasing or current is increasing and resistance is decreasing. So this change in the resistance is directly proportional to the amount of the gas is coming, which is reacting with these oxygens, negatively charged oxygens. So that is the basic principle which works behind the metal oxide semiconductor. But the main problem is that this function will become active only at the high temperature. We have to heat this material to make it working. So for that purpose, we require the micro heater also. So this is showing the basic working mechanism of the metal oxide semiconductor. So if you want to summarize it, what will be the block diagram? So here we can see this is my sensor, which is going to work or which is going to detect the sensor. We have to heat it because as I told you, because this chemical gas sensor or metal oxide sensor will become active only at the high temperature, not at the room temperature. So we have to heat it. For that, we require a heater. That heater may be bulk or the micro heater, but if we want to reduce its power, so we have to, if we are going towards the MEM side, we have to develop it the micro heater. And to determine its change of the resistance, we require a ASIC, that is application specific integrated circuit, which will detect the change in the resistance. And this temperature controller mainly control the temperature of this heater. So this is the complete block diagram of the gas sensor system. Here the thing comes, if we are able to develop this gas sensor platform on the single silicon piece, one side ASIC, another one is the micro heater and sensor. If we are developed onto the single silicon platform, that is known as a monolithic MEMS. And if we are not able to develop, we develop both the things separately, ASIC separate and sensor system separate. And if we combine, that is known as a hybrid MEMS. So this MEMS can be developed into two parts. First is the monolithic and another one is the hybrid. So here first we will try to focus onto the sensor material, how to optimize, how to fabricate, what are the process parameters. And in the second part, we try to develop the heater. What are the heater, micro heater, what are the different specifications, how we design and develop the micro heater. Fine. The ASIC part I'm not going to cover because otherwise the talk will be too much large if we develop this ASIC part over here. So we try to focus this first on the gas sensor. So as I told you, for development of the gas sensors, most across the world, most of the people use basically metal oxide materials, right? Now there are if we go in the metal oxide semiconductors, there are different types of the metal oxide presence. For example, zinc oxide is there, titanium dioxide, tungsten oxide, indium oxide, iron oxide, tin oxide, or there are certain kind, these are the N-type material. There may be certain kind of the P-type materials are also there. But across the world, if we see 37% for the sensors, we use the tin oxide because of its fascinating properties. And second one comes onto the zinc oxide. Now, whenever we want to use the particular kind of the metal oxide, its structure is also different. That's why I gave the talk of my topic of my talk is basically nanostructures. So we can develop the tin oxide nanostructure either in the form of thin film, nanowires, nanotubes, quantum dots. There are different types of the nanostructure we can form. Yes, anybody?
Good morning to all the dignitaries on the dais, guests, student, teaching staff. It's a great joy and the immense pleasure. I feel privileged to extend my warm welcome to all the present here. To feel the
Sanju ma'am, this noise is coming.
To all the present here for the celebration.
Stop. Sorry, sir. I am seeing some of the. Yes, sir. You unmute yourself. I have muted all. Bagga sir, you unmute yourself. I have to press mute all. Participants, please keep your mic on mute while the session is going on.
My voice is audible?
Yes, yes, sir.
Okay. So this is the worldwide study of the different types of the metal oxide semiconductor gas sensors which people have used. Here we can see around 38% peoples are using basically tin oxide for the development of the gas sensors. And second one is the zinc oxide. So if we want to develop yes. So if we want to develop a gas sensors, most of the people are basically using tin oxide. That's why in this present work, we are going to develop the tin oxide based material. And we may have the different type of the nanostructures, like we may have the thin film, we may have the nanospheres, we may have the nanorods, we may have the quantum dots. But in this work, we are mainly focusing onto the thin film. Fine. So the thing again comes, what may be the different types of the technique to develop the tin oxide? Yes, among the participants, can you tell me what are the different techniques to develop the tin oxide, metal oxide materials?
So using sol gel technique also, and for forming film, I have used electron beam evaporation also.
Okay, okay. So good. There may be plenty of techniques. We can, if you want to bifurcate, then it may be the two parts. First is the chemical route for the synthesis. Another one is the physical route for the synthesis. If we see in the chemical route, we may have the sol gel, we may have the pyrolysis, we may have the different types of the film consist on the like precipitation method, or there are different types of the techniques exist if we are going towards this chemical route. If we are going into the physical, then we may have the evaporation, e-beam evaporation, as you told, thermal evaporation may be there, sputtering may be there. But whenever we want to develop the MEMS, for development of MEMS, we have to see the technique which is also compatible to development of the ASIC, that is basically CMOS. ASIC is designed using the CMOS technology, that is complementary metal oxide semiconductor circuit. So the technique should be compatible with the CMOS. And whenever we want to fabricate the IC, the techniques which are used either CVD or the sputtering. So therefore, in this work, we have tried to develop the sensors using the RF sputtering technique. Fine. Sputtering can be, as you know, bifurcated into two parts, DC sputtering or the RF sputtering. DC sputtering basically have the limitation when we are going toward the insulator, because metal oxide is nothing but metal oxide semiconductor. It has a wide band gap material. So here we are going to use the RF sputtering. In RF, that is also reactive. There are two kinds of the sputtering may be there. One is the reactive, another one is a non-reactive. Reactive, where we are using the reactive gases to deposit the films. So here we have used the RF sputtering, that is also reactive, means we are using the combination of the argon and oxygen as a mixture. So let me explain you the process, how are we going to fabricate the film. So this is the system that is consist on the RF sputtering system. Here we can see it. It is basically consist onto the, this is the system where we have to deposit the film. One side is the substrate, another one side is the target. Target was basically of the tin oxide. This is our matching network. Matching network is basically used because whenever the sputtering happens, the impedance of the target changes. And this matching network try to alter its impedance so that maximum power transfer can be take place from power source toward the system. So therefore we have to use the matching network it over here. And these are the cylinder which are used. Basically, one is the oxygen cylinder, another one is the organ gas, because whenever we want to use the sputtering, we have to use the gases, that is inert gas, and we are using the oxygen. That's why we are calling it as a reactive sputtering. And its ratio are set basically through the mass flow controllers, MFC, which is generally called. Now, if we see the what can be of the parameters may be there, because कोई भी जब अपन फिल्म डेवलप करेंगे या कोई भी नैनो स्ट्रक्चर फॉर्मेशन करेंगे, क्या आउटकम होगा? And in every experiment, we get different kind of the film properties. The process parameter may be power, operating pressure. So if we change the substrate, that is also basically change the property. Organ to oxygen ratio, basically if we change its ratio, then property of oxygen concentration may be changed. Pre-sputtering time, that does not influence so much, but yes, to avoid the debris which comes into whenever we keep the system idle, the dust particle that avoid by using the pre-sputtering time. Target, again we are using that because we can deposit using the tin also by varying the oxygen concentration, but here we have used the tin oxide target. Target purity is 99%. So, and the process parameter may be substrate to target distance, power, pressure, and deposition time, substrate temperature. Here, apart from that, we have varied two parameters. I am not showing to all parameter variation. I am showing you only the two parameter variation. In the first set of experiment, deposition time was varied from 10 to 50 minutes, while substrate temperature kept constant. First, we deposit these films, then optimize it, and then we will fix what deposition time we have to kept. And in the second set of the experiment, the optimized deposition time, using that optimized deposition time, we deposit the film by varying the substrate temperature from room temperature to 400 degrees centigrade. And we are keeping the deposition time 45-minute constant because that we have optimized by using the first sort of experiment. So I have bifurcated my process parameter optimization to two parts. First set, we are going to vary the time. In the second set, we are going to vary the substrate temperature. So whenever we obtain the film, our first target is to keep what is the thickness of the film, because that we are varying the deposition time. Thickness of the film can be varied by different types of the techniques. Here we have used the profilometry as well as ellipsometry to determining the thickness of the film. And we have confirmed by both the techniques, which shows that there is a linear relationship between the thickness and the deposition time, approximately linear we can see. This black dot are the profilometer and second one is the ellipsometer. I think most of you know about the profilometer. And for second set of experiment, we have varied that substrate temperature, we have varied from room temperature to the 400 degrees centigrade, and we can say the thickness is almost constant, but there is slightly variation, very minutely. That comes because whenever we deposit at the high value of the temperature, the packing density of the film increases because the material which is coming onto the substrate may go into the more thermodynamically side. So packing density is going to increase a lot. So there is a slight variation in the thickness with the substrate temperature. When we are increasing the substrate temperature, the thickness is slightly reducing, not too much, slight reduction is there. That is first part, because the parameter which we have varied, what is their effect? And second thing we see, when we deposit, because it's a mixture kind of the film, because tin and oxygen, there are two things. Its composition can be measured using the index, but index only gives you the information about the surface composition. But if you want to see across the depth, how these things are deposited, what is the ratio of the oxygen and tin across the thickness. So that has been measured using the SIMS. SIMS is basically known as a secondary ion mass spectroscopy system. What it does, we use the film and by using the high ion beam, we bombard it, and the ions coming which detect or detected using the mass spectroscopy system. And here we can see in the surface, there is no amount of the silicon is not too much. While oxygen and tin we can see smooth are there across the thickness. And when it is reaches to substrate, suddenly silicon increases and tin and oxygen decreases over here. So this is known as a secondary ion mass spectroscopy system. In India, only few places this facility is available. One is the NPL Delhi, I think, and another one is the IGCAR Kalpakkam. So there we can determine how uniform our film is deposited. That can be determined using the SIMS, that is composition analysis using the SIMS. Next, we do its structure analysis. Structure analysis, most of you know what is the structure analysis. Structure analysis we do to see in which direction our film crystals are oriented. For doing the XRD, or that is XRD, we have varied for different films which are deposited from 10 to the 50 minutes, 100 nanometer, 220 nanometer, 320, 470 and 550 nanometer. We have without annealing, we have make two sets of experiment, that is with annealing and that is without annealing and with annealing. Here we can see as we are annealing the film, the sharpness of the films are increases. Sharpness are increasing means its grain size is increasing. We can see it using the Debye shear formula. We can calculate the thickness. Here we can see the peak are less broadening, while here the same peak is less broadened, means the grain size is increasing, which is indicating. For all the films, we have annealed it for 2 hours at 400 degrees centigrade in the ambient atmosphere. So here we can see as we are annealing the film, the sharpness of the peaks is increasing for different films. And in the second set, for the films deposited at the different temperature, we have again it's characterized it. Here we can see without annealing, peak is bit smaller, while after annealing, peak is becoming sharper. Why? Because when we anneal the film, the grains coming close to each other and they merge according to our basic thin film phenomena. So the peaks are becoming sharper after annealing at the high value of the temperature as compared to the normal. And as we substrate temperature has a great influence on the microstructure of the film, because when we see it at the normal room temperature, the material comes, the atom of the materials comes onto the substrate, and that they don't deposit because they get the energy from the substrate because of the heating, and they go onto the thermodynamically stable side to see it, while without substrate temperature they go and deposit onto the substrate. That's why we are getting the higher peak of the films at the high value of the temperature as compared to the room temperature. Now then we go into the for the microstructure analysis. Microstructure, that is nothing but a scanning electron microscopy. Here we can see when we are increasing the thickness of the film, our grain size are bit increasing. These are the grains which I show you earlier, how the oxygen will comes into the contact of this. Grain size is increasing. While we increase, we have optimized this. Later on, you will be able to understand why I have kept the thickness 470 nanometer. And when we increase the substrate temperature at the 470 nanometer film, here we can see the grain size is further increasing, but there is slightly change at the 200 degree centigrade. Why it comes, that I will explain you soon. Why this structure comes, because tin has the annealing melting point at the 232 degree centigrade. Because of this change of the microstructure or change in the melting point, we are altering its property at the 300 degree centigrade we are obtaining. If we are increasing further, the grain size are increasing further. For further analysis, how this grain size are changing or how the structure is changing, we have done the cross-sectional SEM also, that I will show you soon. So here we can say as we are increasing the thickness, our grain size is increasing. While when we increase the substrate temperature, there is decrease in the grain size at 300 degree centigrade. Why? Because tin has a 232 degree melting point, and that's why we are getting the, because of this recrystallization, we are getting the change in the grain size at 300 degree centigrade. To study how these are deposited across the cross sectional, we can see we have what we have done, we have cut it and we have polished it using the gold and the carbon paper, and here we can see when I am increasing the substrate temperature, as I told you, as we have seen already in the structure analysis, we are getting the sharper peaks. So here we can say we are getting the columnar structure and the column distance is decreasing as we are increasing the substrate temperature. It is becoming more dense. Here we can see the film deposited at the 400 degree centigrade is too much dense as compared to the film deposited at the room temperature. And this columnar structure with the gaps going to play a crucial role for the sensitivity. Because whenever we see the sensitivity effect, किसी भी गैस की sensitivity अगर अपने को देखनी है तो उसमें grain size रोल प्ले करता है, देन आपका क्रिस्टल स्ट्रक्चर रोल प्ले करता है, देन आपकी पोरोसिटी रोल प्ले करती है, दैट प्लेंटी ऑफ इफेक्ट कम्स इनटू द पिक्चर. सो हियर वी कैन सी आवर फिल्म इज बिकमिंग लेस पोरस व्हेन वी आर गोइंग टुवर्ड्स द higher deposition temperature. But for the sensing application, our film should be high porous. So that's why we have chosen this 470 nanometer film for deposition at the different substrate temperatures. But this is giving me the qualitative analysis. To quantify it, we have to do some other experiment. To convert it, what we have done, we have used the optical properties, because all of you know, if the material is too much dense, its refractive index will be higher, while if the material is less dense, its refractive index will be lower. So by measuring the refractive index, we can say the film particularly is more porous, so we are able to correlate sensing with the optical properties. For determining the optical properties, we have used the ellipsometry. For that, 4-layer model is used. Basically, silicon substrate we have taken, silicon oxide interface layer. This is the tin oxide layer, and further is that Bergman approximations we have used. So that top layer will consist on the voids plus tin oxide, and that we have simulated. This is the chi and delta, which is showing the perfect match. And this is the refractive index with the wavelength. Here we can see the film of 470 nanometer approximately is giving me the lowest value of the refractive index. It is giving me the lowest value of the refractive index, while the film, which is the thinnest film, giving me the high value of the refractive index. So by picking this refractive index and a particular wavelength, that is we have taken at the 623, because most of the ellipsometer consists onto the 632 nanometer. Thereby we have measured, we have compared the film at the 632 nanometer. And we can, using the Bergman effective media approximation, we can convert this refractive index into the terms of the porosity, that is P. P is the porosity, Nd is the refractive index of the non-porous material, Nv is the refractive index of the substrate that fills the pore, or for the air is used here for calculation. While Np is the average refractive index of the composite considering all the components. Here we have used the Nd 2.041 at 632 nanometer. We have compared the films at 632 nanometer because most of the ellipsometry use the light at the 632 nanometers. And then we have correlated what we have obtained. We have obtained that refractive index is decreasing as our thickness is increasing. And we are getting the minimum value for the refractive index for the film of the 470 nanometer. So which is indicating it should have the highest value of the porosity, which has the lowest value of the refractive index. So we are getting the highest porosity, and this can be visualized also using the cross-sectional SEM over here. These are the cross-sectional SEM, which is indicating it has a higher pores are there as compared to the film deposited at the 470 degrees centigrade, 400 degrees centigrade. Second thing we have again done for the different room temperature deposited film. Here we can see the film deposited at the higher degree, 400 degree, giving me the highest value of the refractive index. Similarly, we have converted into the porosity, so we can see it over here. The film deposited at the 400 degree centigrade has the lowest value of the porosity and the highest value of the refractive index. So because density is increasing, obvious refractive index will increase and porosity will decrease. Then these same can be correlated again using the 4-point probe technique, resistivity measurement. We can see the resistivity is almost constant, but it is suddenly increasing at the 400 degree centigrade, the 470 nanometer film, because of the high value of the pores are there. And similarly, as we are increasing the substrate temperature, the resistivity is sharply decreasing because refractive index has increasing, density is increasing, so grains are too much correlated near to each other, so their resistivity will be low. Then we have calibrated all the films with respect to the LPG. How they are behaving with the when we are exposing with the LPG. Here we can see the film of the 470 nanometer, that is blue one, at different temperatures. हमने अलग-अलग temperatures में उसको test किया. At 400 degrees centigrade, if we see, we are getting the film deposit of 470 nanometer giving me the highest value of the sensitivity. Why? Because it has a higher porosity. That's why we are getting the highest value of the sensitivity. If we see for the film deposited at the different temperature, so here the film deposited at the room temperature is near around for all the different three up to 300 degrees centigrade. Why? Because when we are heating it, this, its crystallinity is improving, because sensitivity does not depend purely on the porosity. It depends upon it also depends upon the crystallinity, grain size, as well as porosity. So when we are increasing the substrate temperature, crystallinity is increasing, grain size is increasing, but porosity is decreasing. So they are complementing to each other. So that's why there is no so much variation. But at this 400 degrees centigrade, porosity is drastically reduced. That's why we are getting the very low value of the sensitivity for the film deposited at the 400 degrees centigrade. And if we correlate with the sensitivity and LPG sensitivity, here we can see the film well behaving with the porosity. It purely depending upon to the porosity as compared to the other parameters. While if we see the film deposited for the different substrate temperature, as substrate temperature is increasing, the porosity is decreasing. At the same time, LPG sensitivity is also decreasing. Now, thing comes how this sensing mechanism happens. Now, if the normal operating temperature tin oxide material is surrounded by the electrically neutral oxygen and temperature increases, neutrally oxygen is converted into negatively charged species. And there are basically two phenomena. One is the physisorption, another one is the chemisorption. The oxygen physisorption happens at the 80 degrees centigrade and converted into the O -2 at 150 degrees centigrade. As temperature increases further, O negative twice is converted into the O negative, and at the same time, oxygen desorption also occurs at more than 600 degrees centigrade due to the thermal reduction of the tin oxide material. The oxygen molecule adsorbed on the tin oxide surface extract the electron from conduction band, which result the creation of the adsorbed oxygen on the tin oxide surface and generation of the depletion region. As I explained you, the variation in the Schottky barrier height. The oxygen adaptation process decreases the electron concentration, which result in the height of the barrier increases. Now, if the distance between the tin oxide column is large, that is porosity, thereby oxygen will able to diffuse more freely and increase the sensor resistance will be higher as compared to the less porous structure. When it's exposed to this LPG, this adsorbs oxygens, it liberates the electron, so conductivity increases or the resistance decreases. This decrease in the resistance due to decrease in the depletion layer width and reduction is the height of the Schottky barrier. So that is up to now how we have deposited the film, how we have characterized the film, how we can optimize all sort of the process parameter. I have taken the two examples. Any doubt to anybody up to now? Any question? If you have, then we go into the micro heater fabrication part. Yes, any query? My voice is audible?
Yes, sir, you are audible.
Yes, any query to anybody? Yes, participants, any query to anybody? If you want to ask something from this part.
No, sir. Thank you so much.
Okay, let me go into the. Now, as I explained you, whenever we want to develop any kind of the sensor, MEMS-based sensors, we have to heat that material. For heating, we can do using the bulk heater. For the characterization, we have used the bulk heater. But when we want to develop a device, we have to develop the micro heater also. For development of the micro heater, there are two kinds of the micro heater consist. One is the that we can say basically membrane type. Two types of there, suspended membrane type or the closed membrane type. The suspended membrane has the less connectivity. It can be visualized from here. So this one is the closed membrane type of the gas sensor, and that one is the suspended membrane. Suspended in the sense कि जिसके के अंदर अपन सस्पेंशन बीम यूज करेंगे और जो मेरा सेंसर होगा वो सेंटर में लगेगा. दिस इज द सेंटर पार्ट वेयर वी आर गोइंग टू फैब्रिकेट द हीटर एंड द सेंसर. While in the closed membrane type, there may be two approaches. One is the vertical approach. Vertical में होगा नीचे अपन हीटर लगाया, ऊपर मटेरियल लगाया, उसके ऊपर थर्मामीटर लगाया. जबकि हॉरिजॉन्टल अप्रोच में सारी चीजें अपन एक प्लेन में लगाएंगे. दैट्स व्हाई वी आर कॉल इट आल्सो एज अ कोप्लेनर प्लेटफॉर्म. So micro heater may be classified into two parts. One is the closed membrane type, another one is the suspension type. Suspension means they are supported by the beam on the four corners. These are the suspension. You can see it over here. And this is my active area. In this talk, I will try to explain you how this using horizontal approach, how the micro heater can be developed. So the key component of the micro heater fabrication is the membrane selection. The membrane can be broadly classified in two parts, that is suspended and the closed membranes. The suspended membranes has a lesser connectivity with the bulk, as we have seen, which in turn reduce the power consumption. Because अपन ने directly पूरे system को माइक्रो हीटर के टच में नहीं लाया, इसलिए पावर कंजम्पशन कम हो जाएगा. However, the suspended micro heater has a less mechanical strength. While the closed membrane micro heater can be fabricated by the two approaches, that is, as I told you a few minutes back, one is the vertical approach, stacked, one over each, and second one is the horizontal approach, which is also called basically the coplanar approach. The vertical approach allows the fabrication of the heater, thermometer, and the electrode at the different layers. This approach gives you the better temperature uniformity at the cost of the more process step as compared to the horizontal approach, in which heating element and the electrode exist onto the same plane. This is the basic. Now steps which you are going to use, that is basically lithography steps. Whenever we want to develop any kind of the MEMS, we have to go for the lithography. So coplanar microheater structure gives the less thermal mass, which in turn not only reduce the power consumption, but also reduce the response time also. The maximum operating temperature in the coplanar structure is comparatively less because instead of direct heating of sensing, we are using the coplaning and onto the same surface. High thermal conductivity of the silicon caters the heat transfer from heating element to the sensing layer. Whenever we want to fabricate any kind of the sensor, the important parameter is basically the membrane to heat and ratio, MHR, or the cavity to active area ratio. It has been reported in the literature, it plays a crucial role for the power consumption of the microheater and the robustness of the microheater. If care is less than 1, the heater temperature reduces, which in turn increase the power consumption. While if it is close to 2, it gives you the poor mechanical stability. So therefore, we keep in between 1 and 2 because we want higher mechanical stability as well as the lower power dissipation. These are the certain kind of the geometry for the micro heater which can be used. Here for A1 is the Mender type, Mender with rounded corner, S-shaped is there, S-shaped with rounded corners is there, double spiral, circular. There may be regular geometry or there may be irregular geometry. But in most of the designs, we try to prefer the regular geometry because whenever we are going to fabricate it, it requires more steps if the design is complex. So we tried to use the simpler one. In this one, we have used the basically meander type. For optimization of its dimensions, we have used the console so that its dimension can be optimized. So the device structure is 4 mm by 4 mm. These are the pads which are basically consist of the titanium gold, and this is our interdigited electrodes. The question comes, what is the use of this electrode? We are going to deposit the tin oxide film onto this surface, and by probing it we can measure the how much change of the resistance is going to happen when we are going to expose this film. And this is our heater. We will heat from here and it will go towards this. So this is his cross-sectional view. Here we can see this is basically the silicon dioxide, which is going to use the passivation layer. And this is our silicon substrate, silicon wafer we are going to use. And we will try to optimize to see the effect of this thickness of silicon underneath of the silicon. This is nichrome heating alloy, which you can see it over here. That is their cross-sectional view. And these are the gold pads to take out the or to measure the resistance and to give the power. Gold contact pads. The thing comes, which kind of the material can be used for selection of the microheater. We may have the different types of the material. For example, we may have the aluminium, gold, platinum, molybdenum, tungsten, nickel or nickel alloy. People have used earlier the aluminium, but the aluminium has the low resistivity. That's why it requires the high power consumption. Gold and titanium are also basically used. These are we have used for the purpose of the contact formation. Gold we can't use because of the low resistivity, while the titanium requires the high melting point. People use extensively the platinum. Platinum gives you the advantage nut material. It does not affect by the oxidizing atmosphere. People use extensively, but the main problem with the platinum is the cost. When we want to develop the low cost gas sensor, we can't go for the platinum. Molybdenum, tungsten are also the high temperature melting point. People avoid it. Therefore, in the present work, we have used the nichrome, that is basically nickel and alloy. Nickel plus chromium is basically nichrome alloy. Nichrome we have used to develop the coplanar microheater platform because it can be used as a high resistivity and it has a low cost. Now the process starts how to develop the microheater using the lithography process. Here we can see in the first part we use basically the 2-inch silicon wafer. The first step prior to any kind of the lithography step is the cleaning of the wafer. We have done the cleaning using a RCA cleaning, Piranha cleaning of the silicon wafer. In the second part, we are going to oxide this. Oxide is the formation of the silicon dioxide, which is going to work like a passivation layer. Then patterning of silicon wafer using the alignment mark first. Then grid delineation, cavity formation, nichrome layer deposition, deposition of the SiO2, opening of the pads and deposition of the sensing layer is the last. These are the some standard protocol which we are going to follow to develop the any kind of the microheater. And here all these are basically अलग-अलग तरह के mask अपन अलग-अलग purpose से लेंगे by using the lithography steps. How we start? We start with the silicon wafer which thickness is approximately 360 micrometer. N-type silicon which has the resistivity of 1 to 10 ohm centimeter, and it is clean first using the RCA1 and RCA2. Then second one, it is oxides. Oxide using the thermal oxidation. Oxidation कैसे किया? इसका oxidation करने के लिए दोनों dry oxidation and the wet oxidation. This oxide at the 1100 degree centigrade in the duration of the 10 minutes dry, 140 minutes wet and the 10 minutes dry. Why we have used this? Because whenever we are going to oxide this, dry oxidation gives you the better quality of the silicon dioxide, but it takes more time. So therefore, in both the side we have used the dry, and in between we have sandwiched the oxide developed using the wet oxidation technique. How after developing the oxide silicon wafer with oxide on both the sides, how we go for the lithography steps? For the first lithography step, we have to create the alignment mark. For that, what can be done? This, in order to create the alignment mark, the oxide's wafer is coated with the positive photoresist. This is spin coater. This is the schematic diagram of the spin coater. Here we can see. This is our vacuum chuck. This is vacuum chuck. We keep the wafer over here. we put the photoresist on the surface and we move it. So due to this centrifugal, it is uniformly coated this wafer with the positive photoresist. This is the schematic diagram of the spin coater which is available in the Siri Pilani. So the spin rate of the spin coater is kept at 4500 RPM for 30 seconds to obtain the 1 micrometer thick positive photoresist. The photoresist is coated on the both side of the wafer to protect the silicon dioxide from the etching. Photoresist क्यों किया? उसको कोट करने से रहेगा उसके अंदर अपना जो ऑक्साइड रहेगा वो इंटेक्ट रहेगा. Then, as you know, the lithography has a certain steps. This photoresist coated wafer are pre-baked at 90 degree centigrade for 30 minutes. 90 डिग्री पे इसको 30 मिनट के लिए प्री बेक किया. प्री बेक करने का फायदा क्या होता है? जिससे क्या होगा, प्रॉपर्ली आपका जो फोटो रेजिस्ट है वो सबस्ट्रेट के साथ में एडहेयर हो जाए सिलिकॉन डाइऑक्साइड के ऊपर जो अपन इसको डिपॉजिट किया एंड बिट हार्ड हो जाए. देन अब जब भी अपने को कोई भी सेंसर बनाना है या माइक्रो हीटर या कोई भी स्ट्रक्चर लिथोग्राफी से बनाना है, फर्स्ट स्टेप वी विल हैव द डिफरेंट टाइप्स ऑफ द मास्क. मास्क आर बेसिकली डिजाइन यूजिंग द क्रोमियम मटेरियल. सो वो वेफर को जो जिस पे फोटोरेसिस्ट कोट किया है उस पे मैंने मास्क रखा. दैट इज फर्स्ट लेवल ऑफ द मास्क. दैट जीएस मींस गैस सेंसर नंबर 1 नंबर मास्क. इसको यूवी लाइट से एक्सपोज किया. ठीक है. अब पॉजिटिव फोटोरेसिस्ट में क्या होता है, जहां पर लाइट जाएगी वो पार्ट आपका सॉफ्ट हो जाएगा, बाकी पार्ट आपका हार्ड रहेगा. Then it has been developed using the developer solution diluted in the DI water. Then wafer are cleaned with DI water prior to the post baking. Post baking होता है एक्सपोज करने के बाद आप उसको हीट करोगे at 120 डिग्री for 40 minutes. Then अब अपने को क्या करना है, उस पार्ट से ऑक्सीजन ऑक्साइड हटाना है, बिकॉज तभी अपन डेप्थ सिलिकॉन तक पहुंच पाएंगे. Buffer oxide etchant is used to etch the oxide from the wafer surface, and the etch rate of the BO is 800 angstrom to 900 depends per minute, and it takes approximately 9 to 10 minute time to etch the 1 micron oxide from the surface, because we have kept the thickness of the oxide is 1 micron. So first we have etched completely silicon dioxide, but this is going to work like a passivation layer. Then once we have removed that oxide, then we have etched the silicon, because then silicon is etched from the pattern silicon wafer to create the alignment mark. Because आगे के प्रोसेस में जो अपन अलग अलग मास्क यूज करेंगे, अलाइनमेंट करने के लिए अलाइनमेंट मास्क लगाने पड़ेंगे. सो दिस इज द अलाइनमेंट मार्क. सो अपने को पता रहेगा अलाइन करने के सेंसर्स के फर्दर मास्क को काम आती है. पहली स्टेप होती है अलाइनमेंट मार्क क्रिएट करना. यूजिंग द TMAH सॉल्यूशन से उसको अलाइनमेंट मार्क क्रिएट करें. TMAH जो सॉल्यूशन है टेट्रामिथाइल अमोनियम हाइड्रोक्साइड which is used to etch the silicon, and etch rate depends upon to the temperature. ये टेम्परेचर पे डिपेंड करेगा कि etch rate approximately 0.3 माइक्रोमीटर at 75 डिग्री सेंटीग्रेड, and the silicon is etched for 2 hours at 75 degree to create the 35 micron diform. जो 35 माइक्रोन जो थिकनेस बचेगी सिलिकॉन की, जो अपने 360 नैनोमीटर लेके चले थे, तो अभी एक तरफ से अपन ने केवल उसको 35 माइक्रोन का डायफॉर्म क्रिएट किया है. द एचिंग डेप्थ इज कंफर्म. इसके लिए अपन माइक्रोस्कोप यूज करते हैं, उसकी डेप्थ कितनी डेप्थ तक एच किया. सो ये कहलाती है फर्स्ट लेवल ऑफ लिथोग्राफी. हर डिवाइस के लिए अलग अलग लेवल्स की लिथोग्राफी होगी. सो दिस इज द इमेज ऑफ द वेफर. ये अपना 2 इंच का वेफर जो लेके चले थे, यहाँ पे आप देख सकते हो कि चारों कोने पे अपन ने अलाइनमेंट मार्क क्रिएट कर दिए. These are the alignment marks on all 4 corners of the wafer at 90 degree. सेकेंड लेवल पे सेम स्टेप्स अपन फॉलो करेंगे. फोटोरेसिस्ट को कोट करेंगे, प्री बेक करेंगे, पोस्ट बेक करेंगे, एंड देन वी ट्राई टू सी These are the grid alignation कि अपने जो डिवाइस होंगी, बिकॉज 2 इंच के वेपर में अपन 81 डिवाइसेस फॉर्मेशन कर सकते हैं. तो एक तरह की अरे फॉर्म कर रहे हैं जो कि ये डिवाइसेस फॉर्मेशन होगा. ये सब जगह डिवाइस लगेंगे, आगे आपको दिखाएंगे ये चीज. So the second level lithography is used to make the grid analysis on the silicon wafer. The size of the device is kept by 4 mm by 4 mm. Therefore 9 by 9 array is created by the lithography process. यहाँ के लिए जो mask यूज किया वो GS2 mask होगा. So this is the diagram or picture of the wafer after second level of lithography. यहाँ पे आप देख सकते हो लाइंस बनी हुई हैं. जो नेक्स्ट होगा उसके अंदर कैविटी फॉर्मेशन. The cavity on the wafer surface is formed using the third level of the lithography. थर्ड लेवल के लिए अपने मास्क यूज करेंगे थर्ड लेवल वाला, थर्ड लेवल मास्क, और विंडो रखेंगे 2 mm, उसको मींस वी विल कीप द 2.45, तो सेंटर में जाकर के वो 2 mm की हो जाएगी। इसके लिए सिलिकॉन डाइऑक्साइड को एच करेंगे BOE सॉल्यूशन से, और लेटर वी एच द 325 माइक्रोन सिलिकॉन इन डेप्थ। क्यों करा? बिकॉज पहले अपन ने 35 माइक्रोन एच किया था, अब 325, तो टोटल पूरा जो अलाइनमेंट मार्क होंगे दैट विल बी गो थ्रू इन दिस स्टेप। इट टेक्स अप्रोक्सीमेटली 14 आवर्स टू ईच 325 माइक्रोन सिलिकॉन। 14 घंटे ओवरनाइट लगता है 325 माइक्रोन सिलिकॉन को रिमूव करने के लिए। दैट इज डन यूजिंग द थर्ड लेवल ऑफ लिथोग्राफी। हियर वी कैन सी these are the windows where we are going to fabricate further the micro heater structure. Next step, we deposit the nichrome is deposited on the opposite side, back of the cavity, using the DC sputtering with thickness of the 0.2 micrometer after cleaning process. GS2 level mask is used to make the grid realignation for defining the device area on the deposit nichrome layer. The dummy wafer, we always attach a dummy wafer because whenever we are going to put onto the स्पिन कोटर, तो जो स्पिन कोटर वैक्यूम सक करेगा, अगर डायरेक्टली वेफर को अपन करेंगे देयर इज अ पॉसिबिलिटी ऑफ द क्रैक। सो इसलिए क्या करते हैं, डमी वेफर अटैच कर देते हैं सिलिकॉन के साथ में यूजिंग द फोटोरेसिस्ट, सो दैट कि वैक्यूम चेक पे वो टूटे ना। Nichrome etching is done using the nichrome etchant with the etch rate of the 50 angstrom per second at 40 degrees centigrade. Nichrome etched grid pattern is shown. This is the nichrome etched grid pattern and grid lines. Once nichrome etching is complete, silicon dioxide etched using the buffer oxide etcher and dummy wafer are separated from the wafer after cleaning with the acetone and the DI water. So ये मेरा structure बना क्या? This is the structure which has been formed onto the silicon wafer. ये एक device है. Like this, we can develop the 81 device on a single wafer. So microstructure structure is realized using the fifth level of lithography. Since the structure is coplanar, coplanar का मतलब है एक तरफ तो मेरा माइक्रो हीटर है, this is my heater and this is my interdigital electrodes. The dummy wafer attached with the silicon wafer prior to this level of the lithography also. I just show you the device, then we go on. These are the structure. Here we can see. These are all are the devices. Later on we are going to dice it. ये एक device है अपनी silicon के ऊपर. Here we can see. And this is his zoomed view. This is our heater and this is our interdigital electrode, जिस पर के ऊपर अपन सेंसर को डिपॉजिट करेंगे जो कि जिसका चेंज ऑफ रेजिस्टेंस अपने को डिटरमाइन करना है। इसको हीटिंग के लिए वोल्टेज या करंट अपन यहाँ से दे सकते हैं। इसको हीट करेंगे, हीट यहाँ से यहाँ पहुंचेगी बिकॉज इट्स अ कोप्लेनर टाइप, दोनों एक ही प्लेन में, एंड देन इट विल चेंज इट्स रेजिस्टेंस व्हेनेवर इट विल एक्सपोज टू द गैस। Deposited microheater is coated with the silicon dioxide as the passivation layer using the plasma enhanced chemical vapor deposition. The isolation between the coplanar microheater and the gas sensing layer is done using the deposit oxide layer. To achieve the better electrical conductivity, titanium and gold are deposited using the lift off technique. Pad जो deposit करें वो lift off technique से करें। Lift off means पहले material deposit किया, फिर structure बना के उस नीचे वाले को remove करेंगे तो automatically ऊपर वाला remove हो जाएगा। That is known as a lift off technique. In this lithography, negative photoresist we use in this particularly whenever we are going to use the sixth level of the lithography. There are two kinds of the photoresist, positive photoresist, negative photoresist. We basically use the positive photoresist mostly in most of the work. And sputtering process, which I explained you for the tin oxide material deposition, is used to deposit at the titanium and gold. The titanium and gold thickness is kept at 200 degree and the 2000 angstrom respectively. Why we use the titanium? Because titanium is used to improve the adhesion property of the gold. That's why instead of using only gold, we first deposit the titanium and then gold. So these are our gold contacts. These are the gold contacts. While this is my meander shape micrometer. Nothing comes, wafer पे बना लिया, इसको काटे कैसे? For cutting it for making the different devices, एक में आप देख सकते हो 2 इंच के वेफर में आपके approximately device बनी है 81 devices. But all devices will not have the same properties. There may be variation always come. So laser dicing is used for the device separation from the wafer because the diaphragm thickness is around 35 micrometer. Therefore, mechanical dicing is not a viable option. 35 नैनोमीटर की माइक्रोमीटर की थिकनेस है माइक्रो हीटर की, सो इसलिए अपन लेजर डाइसिंग यूज करनी पड़ेगी इंस्टेड ऑफ द हैंड डाइसिंग और द मैकेनिकल डाइसिंग. द डिवाइस इज बॉन्डेड ऑनटू द TO header बोलते हैं. These are the TO header, TO3. 6 pins होंगे, that will called as a TO6 header. The heating part of the micro heater is bonded with the reference mark with the header while inter-electrode are onto the other side. The heater cap is kept on the device after wire bonding in order to protect the device from getting damaged. So these are the devices which has been developed using the laser dicing. ये आपकी एक इंडिपेंडेंट एक डिवाइस बनेगी. ये जो एक काटी है आपने वेफर के ऊपर से. These are the different devices, cutting devices. नेक्स्ट कम्स कि जो डेवलप किया माइक्रो हीटर उसको करेक्टराइज कैसे करें. उसको करेक्टराइजेशन के लिए सबसे पहले तो अपने को उसकी पिक्चर इमेज ऑब्टेन करनी है. उसकी इमेज करने के लिए अपन यूज करते हैं SCM, दैट इज स्कैनिंग इलेक्ट्रॉन माइक्रोस्कोप. हियर वी कैन सी दिस इज आवर टिन ऑक्साइड मटेरियल. ये सेंसिंग मटेरियल है. ये हीटर है मेरा, दिस इज हीटर एंड दिस इज इंटरडिजिटेड इलेक्ट्रोड्स IED. This is my sensing SnO2 and this is my heater. And these are the dimension after fabrication. Yes, participants, no query is coming. Any doubt to anybody? Participants?
No, sir.
Are you able to understand what I'm saying? Huh?
Yes, sir. Yes, sir.
No, it would be better if somebody queried it, then it will be the two-way interaction. Otherwise, I will complete it and I will finish it up. Yes? Any query to anybody? Okay. So how to characterize it? इसको करेक्टराइज करने के लिए अपने कुछ एक पैरामीटर अपने को डिटरमाइन करने होंगे. पैरामीटर लाइक इसका थर्मल कोफिशिएंट कितना आ रहा है नाइक्रोम का जो अपन ने मटेरियल यूज किया है फॉर डेवलपमेंट ऑफ द माइक्रो हीटर, एंड व्हाट इज द रिलेशन व्हिच वी आर ऑब्टेनिंग विद द टेम्परेचर एंड रेजिस्टेंस. सो द रेजिस्टेंस ऑफ द माइक्रो हीटर इज रिकॉर्डेड एट द वेफर लेवल पे. हमने उसको मेजर करा. वी ऑब्टेन्ड द डिवाइसेस वेरिंग फ्रॉम 250 टू द 300 ओम in most of the micro heater device. And the relation of temperature and resistance determine placing the micro heater को PID temperature controller में ओवन में रखा और then temperature vary करा और देखा उसका resistance कैसे measure करते हैं using the digital multimeter. And then the relation between the temperature and the resistance given by RT equals to R0 into 1 plus delta T. So that what we have obtained R by R0, and this is the temperature, which is we are obtaining approximately linear relation. And this slope of this is basically giving me the TCR of approximately 0.00029 per degree centigrade. That is temperature coefficient of resistance. And electrothermal characterization of fabricator is done. इसके अब हमने electrothermal characterization करी by source, यानी कि इसमें current use करी थी. Here we are not able to obtain the device in the milliwatt because the resistance of the fabricated device were high. If somebody wants to develop it at the milliwatt, then the resistance has to bring it down further. So micro heater is characterized using the constant current source, and the relation between this is, we can say this approximately linear. As we are increasing the current, the temperature is of the device is also increasing. So one side we will apply the current and the heat will go into the another side to heat the tin oxide layer. Next thing what we have plays a crucial role is basically the silicon under the membranes. What is the meaning of silicon under the membranes? I just show you. This is the silicon. So here we can see this is the silicon. under the membrane. And this is what? This is my SiO2, silicon dioxide. If we reduce it, अगर अपन इसको reduce कर लें तो directly जो अपन heat इधर देंगे पूरी की पूरी इधर चली जाएगी. So we can see we have tried to decrease this thickness. इस thickness को अगर मैं 0 कर देता हूँ, but वो device बहुत ज़्यादा fragile हो जाएगी अगर मैं इसको 0 पे ले आता हूँ 35 नैनो माइक्रोमीटर. So we have varied its thickness by etching it. इसको etch कर करके हमने उसको characterize किया, and then I show you what we have obtained. So the membrane thickness below microheater active area plays a crucial role in order to obtain the maximum operating temperature. Therefore, it is important to optimize the silicon thickness under the microheater active area to achieve the desired operating temperature with a low power consumption. The optimization of the silicon thickness under silicon dioxide membrane is performed using the H. उससे नीचे का जो पार्ट था उसको H किया TMHS सॉल्यूशन से, जो कि 35 माइक्रोमीटर अपन ने थिकनेस छोड़ी है. हमने उसको भी अलग अलग थिकनेस पे किया. उसको हम 29 नैनोमीटर पे लाए, 29 माइक्रोमीटर पे 9 माइक्रोमीटर रेस्पेक्टिवली आफ्टर एचिंग. एंड आई शो यू व्हाट वी हैव ऑब्टेन्ड कि जितनी थिकनेस उसकी कम है उतना मेरा हाई टेम्परेचर में तो ऑब्टेन हो रहा है. इफ आर एबल टू रिड्यूस ब्रिंग इट डाउन, अगर इसको 0 पे ले आओ तो मुझे और हाई टेम्परेचर मिल जाएगा. सो दैट व्हाट वी हैव ऑप्टिमाइज्ड कि थिकनेस जितनी ज्यादा कम होगी अंडर द सिलिकॉन डाइऑक्साइड सिलिकॉन की, उतना ज्यादा पावर कंजम्पशन, दैट विल बी सम सॉर्ट ऑफ द सस्पेंडेड काइंड ऑफ द स्ट्रक्चर. सो वी ट्राई टू ऑप्टिमाइज इट कि we can go further. अगर 9 से भी नीचे जा सकते तो पर डिवाइस that devices were breaking down. So that's why we went up to the 9 micron and we have seen कि जितनी ज्यादा thickness कम होगी उतना ज्यादा मेरा डिवाइस हाई टेम्परेचर ऑब्टेन कर पाऊंगा. एंड देन टेम्परेचर मेजरमेंट के लिए मैंने थर्मल कैमरा यूज किया था. हमने थर्मल रिस्पॉन्स ऑफ द माइक्रोमीटर इज रिकॉर्डिंग यूजिंग द हाई परफॉर्मेंस थर्मल इमेजिंग कैमरा. Here we can see one side we are heating and here we can see the distribution of the temperature. Here this is the heater, ये heater है और यहाँ से heat होगा और यहाँ पे heat जाएगी. This here we are depositing our film, tin oxide film, जो कि इसको heat होगी and we will detect how the temperature is varying. This is the thermal image of the microheater at the where we can see we can go up to the 300 degrees centigrade. And then we have varied the sensor resistance कि इसको expose करके देखा हमने LPG से. we see कि जैसे जैसे LPG डाली इसका सेंसर का रेजिस्टेंस डिवाइस का कम होता गया. But here we need to further, there are so many parameters are there because we have to reduce the maximum operating temperature for the sensor, that is tin oxide. We have to reduce its power consumption. There we can go different type of the nanostructure. Here we have to optimize the different dimensions of the microheater. So there are plenty of work can be done to develop the further device. And the final device, as I show you, will be of this part. This is my final device. This is the final device, MEMS based microheater. Here I have not explained you the development of the application specific integrated circuit. That will be complete electronic side, and that is out of this arena. That's why I haven't taught you how to develop the ASIC for that sensor application. If we combine ASIC and this, then it will be consist on to the certain kind of the hybrid MEMS. That's what is all about. Any doubt, any query to anybody, please let me know. Yes. Yes, any doubt to anybody, please ask.
Sir, myself.
Yes, please. Can you speak loudly, beta?
Yeah, sir.
Yeah.
Good evening, sir. Myself, Dr. Gopi Govindan from VSP Engineering College, Karur.
Yeah, please.
Yeah, can we use any other films for this microheater, sir? Other than tin oxide or any other films?
For sensing application you are talking?
Yes, sir.
For sensing application, as I told you, we can use a tin oxide, we can use the zinc oxide, vanadium pentaoxide. There are plenty of metal oxide materials are there. This micro heater development is just to develop, and later on whatsoever film we want to deposit, we can deposit on it. We can develop the nanowires, we can develop the nano rods, any kind of the structure. We can directly fabricate onto it. This whole, these things now actually, Siri Pilani, you must have heard the name. They have the very good facility to develop these sensors. I have worked it over there only. So they have all the lithography processes and step to develop these kind of the sensors. They have the specialized into this.
Okay, sir.
Anybody else?
Participants, either ask your query directly to the expert or you can write down in the chat box.
Anybody?
Sir, I have a question, sir.
Yeah, please.
Sir, can we fabricate the superconductor using this technology, sir?
No, basically, this is just the fabricate development of the sensor. Now, later on, it depends by which technique you are developing your superconductor material that should be compatible with it. The thing only is that, like here we have used the silicon. As I told you, जैसे मैंने शुरू में बताया कि अपन ने इसमें RF स्पटरिंग यूज किया. क्यों? क्योंकि एसिक अगर मैं इसको हाइब्रिड मेम्स बना रहा हूँ या मोनोलिथिक बना रहा हूँ तो एसिक के साथ उसकी कॉम्पिटेबिलिटी होनी चाहिए. अब सुपर कंडक्टर मटेरियल, आप पहला क्वेश्चन ये होगा कौन से सबस्ट्रेट पे डिपॉजिट करोगे. वो सबस्ट्रेट इसका कॉम्पिटेबल होना चाहिए, वो टेक्निक इसके कॉम्पिटेबल होना चाहिए. ये ना हो कि सुपर कंडक्टर बनाने के लिए आप हाई टेम्परेचर पे जा रहे हो. अगर हाई टेम्परेचर पे आप जा रहे हो और वो जो डिवाइसेस है बाकी जो है उस टेम्परेचर को सपोर्ट नहीं कर पाएंगे तो मेल्ट हो जाएंगे वो. दैट प्योरली डिपेंड विच टेक्निक यू आर यूजिंग टू डेवलप बेसिकली द सुपर कंडक्टर. दैट डिपेंड्स ऑन दैट.
So there is one question from a participants.
Yeah, please.
Sensor activity will change based on metal oxides or not?
Pardon, ma'am? Sensor?
Will the sensor activity change based on metal oxides or not?
एक्चुअली कि अपना ये डिपेंड करेगा कि कौन सा मेटल ऑक्साइड मटेरियल अपन यूज कर रहे हैं. लाइक फॉर एग्जांपल अगर मैं बात करूं मुझे हाइड्रोजन सेंसिंग करनी है. Like if you want to sense the hydrogen for like hydrogen based vehicles, then I have to use the palladium doped material, because palladium gives the high value of the sensitivity for particularly for the hydrogen. So it depends upon to the gas, which gas we want to sense. According to that we select the material. Now in most of the sensor we use the tin oxide, but to make it selective for the particular target gas we doped it with the desired material. Now there are different techniques are there for altering the making the selective. For example, temperature modulation is there, or we can dope it with the certain kind of the material or by using the certain filters over that. So it depends upon to the different materials have different sensitivity toward the each gas differently.
Okay. Any other participant? Any other doubt?
Yes, please.
Sir, you most of this is resistor sensor.
Exactly.
Is there any sensor that has a mechanical component associated with it? Because when it sends the sensing in terms of a mechanical motion. Any gas sensor?
Yeah. Good question. Yeah, it is there na. Like, sir, if you go for the acoustic wave-based sensors, there is a change in the frequency. There is a like here in the chemi-resistive sensors, the change in the resistance is going to take place. But in the SAW sensors or like in the thermal sensors, the temperature is going to change. So if we are able to determine the temperature, then we can sense the particular material.
Okay. Then in generally, what is the repeatability of these sensors? Like what if happen over a period of time?
Yeah, that's a good thing. Like there is a problem with the, as I told you now, people are working on it since last 3-4 decades. But still there are few problems exist. For example, these material will be activate only at the high value of the temperature first. Second thing, if we make it and we make it stable, but over the time, because of the continuation exposure to the atmosphere, their resistance varies because oxygen is going to change its continuously its properties. So making it stable is another challenge that is covered by most of the company using the packaging properly. But yes, still it has a limited lifetime. Lot of people are working on it to improve its lifetime.
Thank you, sir. Thank you so much.
Welcome, welcome. Anybody else?
Yes, sir. I have a query.
Yeah, please. Yeah, please.
Sir, okay, I'm sir working on the metal oxide quantum dots for gas sensors applications. My
Okay.
question is this: when the sensor operable at the temperature less than 100 degrees Celsius, the effect of relative humidity on the target gas response properties is significant.
Can you repeat, please?
When the sensors operable at temperatures less than 100 degrees Celsius, the effect of relative humidity on the target gas response properties is significant. How to measure the relative humidity of a sensor to a target gas?
No, for that now what we do generally for making it less sensitive to the humidity, we keep it for few days in the certain atmosphere to make it temperature. Let's say for the 120 degrees centigrade, we keep it the sensor for 3-4 days to make it stable, so that whenever the humidity will come, because humidity is going to play the crucial role for any kind of the metal oxide material. As I mentioned in the pros and cons, there is a effect of the humidity always comes into it. Why? Because whenever it exposed to the oxygen from the atmosphere, it alters its properties, its base resistance. So main task is to either we packed it in such a way so that only the by using the filter only the gas target gas will come into the contact with it, the humidity effect will not come. But certainly humidity affects a lot onto the sensor performance. It is a very much important consideration which we have to consider whenever we want to develop the sensor for the industrial or for the daily use.
Yes, sir. Sir, operating temperature plays an important role in the gas sensing mechanism.
Uh-huh.
Operating
Sorry?
temperature,
Yeah, yes,
plays
yes,
an
yes, yes.
important role in gas sensing mechanism.
Right,
Sir,
right.
if I am doing the gas sensor to a particular target gas less than 100 degrees Celsius or it at room temperature, then relative humidity should be impact on the sensor response.
Effect is that the problem with the metal oxide that they will become active only at the above 200 or the 300 degrees centigrade, depend upon to the type of the gas which you are sensing in most of the material. Now, if we want to reduce its temperature, operating temperature, then we have to either use the polymers instead of metal oxide materials, or we have to go some other types of the materials. But in the metal oxide, there is a limitation that will be activate only at the high temperature. So at the high temperature, the effect of the humidity will not be that much, because as the temperature increases, humidity reduces, all of you know.
Yes, sir.
Yes.
Thank you, sir.
Welcome. Anybody else?
Any participants? Any query? Okay, in case of no further query, I thank you, sir, for this wonderful lecture. Definitely, the participants will going to learn a lot about the MEMS-based case sensors, fabrication.
Excuse me, madam.
Yes.
Yes, please.
Should I ask a question?
Yes,
Yeah,
yes,
please.
sure.
I have heard about the nano heater also. Can you say how the micro heater and nano heater are different in way of functioning?
No, the thing is that, sir, when we are developing here, we have used the dimension of all the device in the micrometer range, right? Correspondingly, the power consumption is there. If we are able to go towards the nano size device, if we are able to develop the micro heater on the nano dimension, then obviously its power consumption will be too much less, and the device compatibility will device size will reduce, and the battery which is connected to heat this, that is also required less power. So overall power consumption will reduce, size will reduce. And all of we know, when we go towards the nano, that is surface to volume ratio. If we are going towards the lower side, surface to volume ratio, then our sensitivity is going to increase because surface area is going to increase as when we are decreasing the size. That's why we may get the high value of the sensitivity and at the same time low value of the power consumption. That's why we can go for the nano heater also. Good question, sir.
Thank you, sir.
Welcome.
Any query? Anyone else? Okay, sir. Then thank you so much.
Thank you, ma'am.
For sparing the time
Thanks
for
for
this.
the participants for listening.
Thank you, sir.
Thank you.
Okay, participants. So tomorrow again we will meet at 10 a.m. for the first session by Professor Kanupriya Sachdeva from MNIT Jaipur. And I have posted the feedback link in the chat box.